hiya, 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 hiya. Today we're going to look at a problem, mechanics problem, that looks at what happens when an object slides off a surface. And in this case, we're going to look at Physics Ninja sliding off the roof here. And the question I'm going to have for you is, so he's going to start at the top. And what's going to happen? Well, he's going to start off pretty slow. He's eventually going to pick up some speed. He's going to be going faster and faster and faster until, oops, at some point, he's going to not be in contact with the surface anymore. Okay, he's going to be going too fast to stay on this circular trajectory. So the goal of this problem here is going to be, let's set up the equations and let's find the angle where Physics Ninja actually loses contact with the surface. Okay, so let's set up the equations and see how we would solve those to obtain this angle. Okay, so let's start off with the free body diagram. So here I've got the same pictures on the previous slide. I've just got the Physics Ninja. This will be the point where he's just about to lose contact with the surface here. So he's got quite a lot of speed. Free body diagram is pretty simple for this object. There's only two forces acting on it. Here we're neglecting friction in this problem. So you simply have force of gravity, mg acting down. Now we also have a contact force. And at some point that force is going to disappear, but let's just add it for now. And our goal is going to try to find the angle at which it disappears. So these are really the only two forces acting on the system. I guess the next thing we could do is remember where the angle theta is. The angle theta is this one here. So on this diagram, this is also the angle theta. Okay, so what I'm going to do now is I'm going to pick a coordinate system. For all of these types of circular motion problems, it's usually good to have a coordinate system where I have one of the axes that's in the direction of the radial direction of the circle. So I'll call that a positive radial direction. And the other direction we'll choose is a tangential direction. We'll call this the positive tangential direction. Okay. So the next step, we simply have to write Newton's second law. So let's start by doing this. So first equation, we'll take the sum of the forces acting along the radial direction. Okay. We have two forces. We have a component of the weight, and the component of the weight that's in the radial direction is going to be mg cos theta. And we have minus the normal. And now we have an object that is moving in a circle, so it's definitely going to have some acceleration in that radial direction. Okay, let me just call that a subscript r. The next equation we have is in the tangential direction. In the tangential direction, we really only have one force. Right? We only have one component of the weight here. Okay. Imagine here I have, this is mg cos theta. That's what we just had. Cos theta. And this tangential component of the weight is mg sine theta. Okay, and that's really the only force, right? There's no normal force, and we're not considering any friction in this problem. Therefore, that's it. So, in the tangential direction, we simply have mg sine theta equals to, again, mass times acceleration, and a different component of the acceleration, the tangential component. Okay, so these are our two equations. Again, now if I look at equation 1, I could fix this right-hand side by noting that the radial acceleration, which we've seen before in a uniform circular motion, although this is not uniform, it still applies instantaneously. The only thing that's different is the speed now changes as Physics Ninja slides down the roof. Okay, so the acceleration, I can replace the value by v squared divided by r. Okay, so let's go back to equation 1 and let me rearrange this. So I'm going to isolate the normal force. Okay. So if I group some terms here, I have mg cos theta minus mv squared over r equals to the normal force. Okay, so this is kind of our important equation here that we're going to try to solve. So remember, when there's no more contact, we're going to have that the normal force is going to be equal to 0. So you can see initially the normal force is quite big. The speed here is small when he's at the top. He's basically not moving, so the normal force is basically simply equal to the weight. The angle is 0, so the normal force would simply be equal to mg. But as he starts to slip, as he starts to pick up speed, actually this term here grows bigger. This term here actually gets smaller as the angle gets larger. And eventually those terms are going to balance out. Okay, and the normal force is going to be equal to 0. So we have to find the angle for which these forces balance out. The complication here is that you can't just isolate the angle theta, because you also have the speed in this expression here. Okay? And we have to find an expression to eliminate the speed and write the speed in terms of the angle theta. So that's what I'm going to do on the next page. And our goal now was to eliminate this second term, or at least to write this second term in terms of the angle theta. Okay. In order to do that, we're going to use a conservation of energy. Okay. So, conservation of energy, of mechanical energy, simply says we look at all the energy when he's at the top of the circle and equate that to all of the energy when he's at this angle theta, and just set those equal to each other. Okay. So conservation of energy. Okay, so at the top we're going to have some gravitational potential energy. He's a certain height above the ground here, so let's call that U at the top. And he basically has no kinetic energy at the top. Right? He's got a very small speed, or basically not moving. So that there has to be equal to the total energy when he's at this position. Okay, so he's still going to have some, let's call that position 2 here. Okay. And he's also going to have some kinetic energy at this point. Okay, so at the top we have an expression for gravitational potential energy. Simply mass times gravity times the height, and the height is the radius of the circle. When he's at position 2, he's still a certain height above the ground, right? This is his height above the ground. Okay, you use a little trigonometry. You know that this is still the radius. That's the height. Therefore, the gravitational energy at that point is simply mg. And the height, I'm just going to right away just write it in terms of the angle theta, is r cos theta. Okay. And plus the kinetic energy term. Okay, so here we have our expression. We have an expression here for mv squared. Equation 1 has an expression for mv squared divided by r. So let's just simplify this expression a little bit. We're going to have mg 1 minus cos theta equals to 1/2 mv squared divided by the radius. Okay. Actually, this 1/2 factor, let's just multiply both sides by 2, and I can eliminate this side here. Okay, so we have mv squared divided by r equals to 2mg 1 minus cos theta. So what we have to do now is simply substitute this into equation 1. Okay, so let's go ahead and do that. Let's call that 1 prime. We have mg cos theta minus 2mg 1 minus cos theta equals to n. The nice thing about this expression here is we have an expression for our normal force, which doesn't now include the velocity term. It only includes the position of Physics Ninja on this circular path. Okay. I can group some of the terms together and rearrange this expression a little bit more. Let's factor out an mg. You have cos theta here. You're going to have 2 cos theta. That's actually 3 cos theta. And you still have a minus 2 in there, equals to the normal force. Okay, the original problem statement was, let's find the angle theta where Physics Ninja loses contact with the surface. Okay, so we have to solve this expression. First, he loses contact with the surface when the normal force equals to 0. Okay, and we see that that's going to happen when this term in the bracket here equals to 0. Okay, so that's what we need to solve. 3 cos theta minus 2 equals to 0, or cos theta equals to 2/3. And lastly, we get an expression for the angle theta. If you solve this, x minus 1 to the 2/3. We substitute that in a calculator, you get approximately 48 degrees is the angle which he leaves the surface, or the normal force equals to 0. Okay, so there you have it, folks. That's how you obtain that angle. The next step I want to do is, well, if you don't want to use conservation of energy to find an expression for velocity squared term, you really don't have to. You can use the second equation that we had, and that was an expression for the tangential acceleration. So let's go ahead and do that. We now want to find an expression for v squared, but say you didn't want to use conservation of energy. I think it's personally the easiest way, but you can also use this expression over here. Right? I mean, we know the acceleration at every point. And the problem with this is that the acceleration changes. Right at the top, the tangential acceleration is basically 0. However, when you start increasing that angle, this term is no longer 0. So we have a term here that gives us the angular acceleration for every single angle. So we just have to work at this a little bit. Okay. You start off by writing the acceleration as the derivative of the velocity. And here we're talking about the tangential velocity, so I'm not going to write the subscript anymore. But that's g sine theta. Okay. The next step I'm going to do is I'm going to multiply both sides by v. Okay. Now I have to simplify this expression a little bit, and I have to use a few little tricks. I want to rewrite this term, which is v times the derivative of the velocity with respect to time. I can rewrite that term as 1/2 dv dt of function called v squared. Right? If you take the derivative of v squared, you get there's a 2 that'll come out, and then you'll get v times the derivative of velocity with respect to time. Okay, so the left-hand side is okay. Now the right-hand side, I have to change this a little bit here. The g doesn't change, that's just a constant. The next term I have is sine theta, and I want to kind of do something similar to what I did here. Actually, what I have to do is rewrite the velocity in terms of the angular velocity. And you're going to see why in a minute. Okay. And again, the angular velocity is not constant. It's always changing, right? It's actually getting faster. But let's rewrite that term, because now I'm going to I can rewrite the angular velocity in terms of the angle theta. Okay. So let's take out the constant terms. G times r sine theta. And this here is d theta dt. Okay. Now again, this right-hand side of the term can be simplified. If I wanted to really factor out the derivative with respect to time, I could do that. The constant terms aren't impacted by that. I can still have gr here. How would you factor out the derivative with respect to time, if you have sine theta here, I want you to think about this for a minute. But if I wrote cos theta, now you can check the answer, right? If you take the derivative with respect to time of this function, you get g times r. The derivative of cos theta gives me minus sine theta, so that'll cancel this minus sine theta. And then at the end, I still have to take the derivative with respect to time of the argument here of theta with respect to time. Okay, so all of this works out. Okay, at the end now, so I'm left with just this expression, 1/2 d over dt of v squared equals d over dt gr minus cos theta. Okay. And one last step, let's just put all the terms together on one side. Again, maybe I'm just going to rearrange this a little bit here just to clean it up, but I'm going to factor out the derivative with respect to time. Let me multiply everything over by 2 also. So this term here will be v squared. When I bring this term on the other side of the equal sign, that negative sign will turn into a plus. And now since I've multiplied through by 2, I have to be a little bit careful here. Okay. And that's it. This here, all of this here has to be equal to 0. The only way that this term here is equal to 0 is if everything in the bracket here is equal to 0 for every single position. This is what you call an invariant with time. Basically doesn't change. It's kind of like an energy term, right? We said the mechanical energy doesn't change with respect to time. That was an invariant with respect to time. So that means if I evaluate this term here at the top of the circle, it has to be equal to this term here evaluated at that angle theta. So let's do that. Let's evaluate this term here at the top of the circle. At the top of the circle, well, there's basically no velocity, right? So there's no v squared term. At the top of the circle, we have cos theta, or theta, which equals to 0. Therefore, this term here becomes 2 gr. Okay. What about now at position where he's just about to slip off the roof? Okay. If you evaluate everything in the bracket at that position, we're going to have a v squared term plus 2g r cos theta. Okay. Again, now if we group together the terms, what we're going to get is an expression for v squared. So 2g r 1 minus cos theta equals to v squared. Okay. Actually, if you go back and double check what our expression was on the previous page, I wrote it as an expression for mv squared divided by r, but you're going to see that the expression for v squared is exactly the same as we have in this case. The only difference is here we worked using the tangential acceleration in order to find an expression for a quantity that was an invariant for every position on this circle. It involves a little bit more mathematical tricks, but it's all pretty straightforward. Okay, I want to leave you here with an experiment here. You see there's a dry ice puck sliding on a hoop. You'll first see it going fast, but now we'll go back frame by frame and have a look at it in slow motion again. This is a direct measurement video from Peter Bohacek. He's a local high school teacher, but have a look at the puck now in this angle. It's going past 45 degrees. Every small line is 1 degree. Now it's hard to see in the zoom-in picture, but certainly right around here, it's kind of left the surface, and certainly past 60 degrees you can see a gap between the puck and the circular hoop. Yeah, it's nicely done. So there you have it. I'd invite you to check out some of the other direct measurement videos that Peter has on his website. Just Google it. There's a lot of really nice physics being done at that high school. Thanks.